Welcome back to Applied Mathematics. In this video, I want to introduce you to the method of elimination, which I mentioned before is the other tool we have for solving a system of linear equations. To see how it works, let's jump to the same system we've solved previously. 2x minus 5y equals 1, 4x minus 3y equals 9. We've looked at the graph of this system and we solved this system using the method of substitution. In both cases, we got the solution 3, 1. Now I want to go through the same system again, this time using the method of elimination. So let me get my head out of the way and we will dive in. Whenever I'm using the method of elimination, I find that it is helpful to label each of the equations in the system. For a system of two equations and two variables, that doesn't really help all that much, but it's a nice habit to get into when you get into more complicated systems. You will find it very easy to lose track of where you've been and where you're trying to go. When you're using the method of elimination, the goal is to eliminate one of the variables. And we eliminate the variable by manipulating the equations so that the coefficients have the same magnitude but opposite sign. It doesn't matter which way you go, but generally speaking, there's going to be one way that's slightly easier and one way that's slightly harder. In this particular example, I might notice the coefficients on x. I have 2 and 4. And 2 times 2 is 4, so that's an easy one to figure out. If I wanted to eliminate y, I'd have to figure out the common multiple between -5 and -3, which is not hard, but a little bit harder. In this case, if I take equation A and multiply by 2, and equation B and multiply by -1, multiplying left and right side of equation A by 2, we're going to end up with 4 times x minus 10 times y equals 2. Multiplying the left and right of equation B by -1, we're going to end up with -4 times x plus 3 times y equals -9. And that is a perfectly valid thing to do. You can multiply both sides of an equation by a non-zero constant, and the equation still has the same truth value. The other thing that you're allowed to do is add the same thing to both sides of an equation, and it will maintain the same truth value. And that's where we're going to be a little bit sneaky. I am going to add to 4x minus 10y equals 2, -9 on both sides. On the left side, I'm going to add it just as -9. On the left, I'm going to add it in the form of -4x plus 3y. Because I have an equation here, -4x plus 3y is -9, and so adding it in either form is adding -9 to both sides of the equation. But because I chose to do it this way, I get some really nice things happening. I have a 4x and a minus 4x. 4x minus 4x is 0x, or just 0. -10y plus 3y is -7y. And then 2 minus 9 is -7. Divide both sides of the equation by -7, and you get that y is equal to 1. Now take that value and plug it into either of the equations that we started with. I'll plug it into the first equation, but it really doesn't matter. When there's a fraction, sometimes you can choose an equation where you notice that you'll multiply and cancel out the denominator and no longer have a fraction. But when you have a whole number to plug in, generally there's not much of a difference. But I plug that in, I get out that x is 3. X is 3, y is 1. That gives us the same solution, 3, 1, that we got using 2 other methods in a previous video. Let's look at one more example just to make sure that that's not a fluke and we really do know what's going on. How about 6x minus 4y equals negative 3, and 5x plus 3y equals 7. Again, I'll label that first equation as A and the second one as B. It's not that confusing, there's only 2 equations, but it's a good habit to get into. We have a choice here of either eliminating x or eliminating y. I notice in this system that the coefficients on y are slightly smaller than the coefficients on x, which means we'll have nicer numbers to work with. I also notice that on y we have a positive and a negative term, which means I don't have to worry about multiplying by negatives. If I take that first equation and multiply by 3, and the second equation and multiply by 4, everything should work out. 3 times 6 is 18x. 3 times minus 4 is minus 12y. And 3 times negative 3 is negative 9. 4 times 5 is 20x. 4 times 3 is plus 12y. And 4 times 7 is 28. Add these together. 18 plus 20 is 38x. Minus 12y plus 12y is 0y, or just 0. And then negative 9 plus 28, or just 28 minus 9, is 19. Get x by itself, divide by 38. That may or may not be one that you know offhand, but it actually works out really nicely. 19 times 2 is 38. So this fraction reduces and becomes 1/2. Now, plug that into one of the equations we started with. It still doesn't matter which one. I will choose the one that has an even coefficient on x, though, because I know that multiplying an even number times 1/2 gives me a whole number. Multiplying an odd number times 1/2 would give me a fraction, and that would make the arithmetic a little bit harder. So I get that y is negative 6 over negative 4, and that fraction reduces and becomes positive 3/2. In this case, my ordered pair is going to be the point 1/2, 3/2. Jason paddled his canoe 24 miles upstream in 4.0 hours. It took him 3.0 hours to paddle back. Assuming that Jason kept a constant paddle speed, determine the speed of the river's flow. Here is an application that is one of the classic examples of where systems of equations can come in handy. Do I expect that anyone here is ever going to need to use this sort of information to calculate the rate of a river's flow? No, probably not. But think about the applications you do care about. Think about where you might have two forces or two currents that oppose each other or maybe help each other. And that's the idea we're going to build on here. So we need a couple of pieces of information. We need the rate formula. Distance is rate times time. Right? For anyone who is studying physics, assuming that Jason kept a constant paddle speed, that tells us, first of all, that this is the equation we can use. I've also got an implicit assumption. Let's assume that the river is flowing at a constant rate. That's actually a fairly good assumption for short periods of time. But now we need a couple of variables. I'm going to use the variable v to represent Jason's speed and the variable u to represent the river flow. Why do we use v? Well, v for velocity. Oftentimes instead of d equals rt, you'll see it written as d equals vt, which is perfectly fine. Why u for the river flow? Well, it's a variable next to v. So when we are going upstream, the river is fighting against Jason, or Jason is fighting against the river. The rate at which Jason is actually moving is the speed at which he is paddling minus the river flow rate. And going downstream, that's when the river is helping. The rate that the canoe is actually traveling is the speed that Jason is paddling plus the river flow rate. So if we look at the upstream circumstance, Jason went 24 miles in 4 hours. So our distance is 24. Our rate going upstream is v minus u, and our time is 4.0 hours. Going downstream, our distance, well, is the same. He went back to where he started. So our distance is again 24. Our speed this time is v plus u, and our time in this case was 3.0 hours. And that is a system of 2 equations in 2 variables. There are a couple of different ways we can solve this system. I'm going to use the method of elimination because I want to use this as an example of how to use elimination to your advantage. But I did want to point out that using substitution is a perfectly valid choice here, and there are certainly times when that might be more helpful. I'm just going to first rewrite this system, distributing and then switching the left and right of the equations. Then from here, I'm going to go back up to the statement of the problem, which I don't quite have enough room for. The problem asks us to determine the speed of the river's flow. The speed of the river's flow is u. We need to know the value of u in order to solve the problem. We don't care about the value of v. And that's something we can use to our advantage in the method of elimination. If we eliminate v first, we will get the value of u. Following the method of elimination from there, we would then plug that value of u into one of the original equations and use that to figure out the value of v. But we don't care about the value of v, so we can skip that step. We can eliminate v, figure out what u is, and stop there without finishing the method of elimination. We will have our result. So to eliminate v, I think I'm going to multiply equation A by positive 3.0 and equation B by negative 4.0. That will give me 12v minus 12u equals 24 times 3.0 is 72. And then we will have negative 12v and negative 12u, and 24 times 4 is 96. Add these together. 12 minus 12 is 0. Negative 12 plus negative 12 is negative 24u. And then 72 minus 96 is negative 24. Divide both sides of the equation by negative 24 and you get that u is 1.0. Now you have to kind of stop and scratch your head and figure out what the units are. Remember that u is a rate of speed. Our distance was given in miles. Our time was given in hours, so the rate must be in miles per hour. The river is flowing at a rate of 1.0 miles per hour. And that's it. We don't need to finish anything. We don't care what v is. We have answered our question. And with that, I think I've talked long enough. We still have higher order systems to talk about, but I'll save that for a future video. For now, thank you as always for joining me, and I'll see you next time.